Hi everyone. So let's solve this multiple choice question based on Ellingham diagram. But before that, let's understand what is Ellingham diagram. So here you can see this is basically Ellingham diagram. And here the graph is in between delta G naught versus T, right? So on y-axis you can see delta G naught, the value is negative, we will understand that part. And here on x-axis temperature is there, right? I'm sure you all have read about this particular equation. Delta G naught is equals to delta H naught minus T delta S naught. And you can derive this equation using second law of thermodynamics. Now let's write this equation like this. Delta G naught is equals to minus delta S naught into T plus delta H naught. Now if we plot delta G naught on y-axis and T on x-axis, here you can see an equation y is equals to mx plus c, which is nothing but the equation for a straight line. So here you can see also the graph is basically what the straight line, right? Delta G naught versus T graph is a straight line where the slope is minus delta S naught and the y-intercept is delta H naught. Let's take one example. In fact, let's take two examples to understand this. Let's take these two examples, right? So first I am taking this particular reaction where 2 magnesium solid plus O2 gas converting into 2 MgO solid, right? Now it's a combustion reaction, and for that we know a combustion reaction is basically it's an exothermic reaction, so delta H naught will be negative. So if we plot a graph of delta G naught versus T for this particular reaction, so the delta H naught or the y-intercept will be negative, which you can see here. It is what? Negative, right? Okay. Now what about delta S naught? So delta S naught, if you see reactant side, we have 1 mole of gas, and product side, only solid is present. So definitely entropy here will be more, and the product side entropy will be what? Less, right? So if we calculate the change in entropy, the delta S naught, the change is basically nothing but final minus initial. So the change will be negative. So delta S naught here will be negative. And what about minus delta S naught? So that will be positive. And here you can see again, minus delta S naught is nothing but the slope. And slope here, it's quite visible. That is positive, right? Now let's take one more example. Let's take 2 zinc solid plus O2 gas giving you 2 ZNO solid. Again, combustion reaction, delta H naught is negative. So you can see here, this is what the y-intercept for this particular reaction. So delta H naught is negative, but one more thing, if you see, delta H naught is less negative. So this value is near by minus 600, and here it is around minus 1100, right? So delta H naught is negative for this particular reaction. What about delta S naught? So that is again using the same concept that we used above. Again, here entropy will be more and here entropy will be less. So delta S naught will be negative. And what about minus delta S naught? So it will be basically positive, right? So again, the slope is positive. But there might be a question in your mind that what about this point? I mean, you see, at this point, slope is changing. So why it is changing and the slope is becoming more? So let's understand that part also. So you see here, this is basically at this point. That means around this temperature, that is around this 800 degrees Celsius, right? The slope for this particular reaction is increasing. Why so? Because around this temperature, zinc actually convert into gas. The boiling point of zinc, cadmium, mercury is actually less. So to zinc, it is gas and plus O2 gas. And this is what 2, I'm sorry. So it will be 2 ZNO solid, right? And if you see, now the zinc is also in the gaseous state. So here in the reactant side, entropy will increase further, right? So entropy will be more in reactant side. The product side entropy will be same. So here the change in entropy will become what? More negative, right? And if it will become more negative, that means minus delta S naught will become more positive. And if it is becoming more positive, that means the slope will what? Increase, right? So I hope you understood that if the slope is changing, that means the phase of one of the reactant is changing at that particular point. Now, one more question can come in your mind that what about this particular reaction? Here, the slope is negative, right? So let's apply the same concept. Here it is 2C solid plus O2 gas and giving you 2CO gas. So here if you see, in the reactant side, we have 1 mole of gaseous molecule, oxygen, and here we have what? 2 moles, right? So the number of gaseous molecule is increasing, so the product side entropy will be more, and in reactant side entropy will be less. So here delta S naught will be positive. In turn, minus delta S naught will be negative, and the slope for this particular reaction is what? Negative, which is quite visible, right, in the Ellingham diagram. One last thing. You may ask that, okay, I understood that delta H naught is y-intercept, but for a particular reaction, y-intercept is constant, right? But we know that delta H naught change when we change temperature. So that is one of the limitation of Ellingham diagram, that the delta H naught and delta S naught, they are constant in a range of what? Temperature, right? So that is, you can see, that's one of the limitation of Ellingham diagram. Now, as we have understood this Ellingham diagram, let's apply how to apply this Ellingham diagram. And once we will learn that application part, we can solve that question easily, right? So let's learn the application part. Again, I am taking these two reactions, right? Okay. So first I'm writing this 2 mg solid plus O2 gas, giving you 2 MgO solid, and let's take some temperature, right? So let's take, what about, let's take some temperature like this, some 500 degrees Celsius. Okay, so if we take 500 degrees Celsius, right? So here you see, okay, I'm just taking this temperature. So at this temperature, if you see, for this, I'm sorry, for this delta G naught is around minus 1000, right? So here if you see, delta G naught is around minus 1000 kilojoule per mole of oxygen, right? And let's talk about this. So for this reaction, 2 zinc solid plus O2 gas, giving you 2 ZNO solid. And for this, if we calculate delta G naught, this is coming at this point, this is around 500, right? Okay, so this is, let's take 500 kilojoule per mole. Now, applying Hess law, if we multiply this reaction by 1, and if we multiply this reaction by minus 1, and if we add, what will happen? You see, oxygen will get cancelled out, so it will become what? 2 mg solid, right? This will be positive, and this ZNO will come left hand side, so it will become what? 2 ZNOs I'm sorry, again, this is 2ZNO solid, right? So this is coming left hand side, and this zinc will go right hand side. So 2Zn solid, and again MgO will remain on the right hand side, 2MgO solid, and oxygen will get cancelled out, right? And if you calculate delta G naught for this reaction, you see minus 1000 plus 500. Why I'm saying plus 500? Because minus 1 multiplied with minus 500 will become what? Plus 500. So it will be minus 500 approximately kilojoule per mole, right? So here you see for this particular reaction, delta G naught is negative. That means the reaction or this particular process is spontaneous. And what is happening in this process? You see, magnesium is able to reduce zinc oxide into Zn, right? So now we will conclude what we are going to conclude. So we are concluding basically any metal which is present in Ellingham diagram at the bottom. Let's talk about this magnesium. So that will be able to reduce any metal oxide which is present above that magnesium, right? So magnesium will be able to reduce Al2O3, right? Of course, below this temperature. Because if you go above this temperature, this for this particular reaction, aluminium will come at the bottom and magnesium will go, or this particular reaction will go above, right? So in that case, basically aluminium, of course, I'm talking about this temperature, right? Above this temperature, aluminium will be able to reduce magnesium oxide. Let's take one more example. Let's take like this again. Let's take, what about magnesium? Will it be able to reduce zinc oxide? Yes, because magnesium is coming below than this particular reaction. What about zinc? Will zinc be able to reduce CO2? Yes. But will copper will be able to reduce zinc oxide? No. Right? So if we talk about this particular temperature, if the graph go above that, then there is a possibility, right? But of course, until this line is below, the line belongs to this copper equation, right? Or the combustion equation for copper. Definitely, copper won't be able to reduce zinc oxide. So I hope you understood how to apply this Ellingham diagram, right? To decide whether which element will be able to reduce which particular element or metal oxide, right? So let's go and go back to this particular question. Now, the correct statement regarding the given Ellingham diagram is, the first statement is at 800 degrees Celsius. So this is around somewhere, I think this is around 800, right? Okay. So 800 degrees Celsius, copper can be used. So this is somewhere, this is what for copper, and here it is what somewhere zinc, right? So copper won't be able to reduce zinc oxide. Zinc will be able to reduce what? Copper oxide, right? Okay, copper 1 oxide. So this is a wrong statement. Now going back, at 500 degrees Celsius, that means we are talking about this particular point. Coke can be used for the extraction of zinc from ZnO. Again, this is here, and for coke line, the point is here. So definitely, coke won't be able to reduce zinc oxide at this particular 500 degrees Celsius, right? Okay. So this is also a wrong statement. Coke cannot be used for the extraction of copper from CO2. Now, for coke, the line is below, and for copper, it is above. So definitely, in this case, coke can reduce copper oxide. So again, I would say that this is a wrong statement. What about this at 1400 degrees Celsius? So somewhere here, 1400 degrees Celsius, aluminium can be used. So this is what the graph for aluminium can be used to reduce. And here it is what for zinc oxide, right? So yes, aluminium will be able to reduce what? Zinc oxide, right? So the fourth statement is the right statement, and that will be the answer for this question, right? I hope you understood this. Thank you.